All right. So, once again, I think all of you know that it's the start of World Space Week today. So, we had Karthik's talk as actually the start of the entire World Space Week because it's also really apt for the theme. If you go to worldspaceweek.org, the theme for this year is actually satellites and how satellites make our life better, but also the physics of it.
Once again,
1 minute.
I think all.
Yeah, sorry. So basically, I think it's going to be very apt for today for this year's theme. So let's get started. And some of you don't know Karthik yet. Karthik Tawari, he's a student at Ashoka University, and he's majoring in physics and philosophy. So those of you who are on Discord, you can get in touch with him later as well. So yeah, let's get started. It started to record, I think. Okay, and I think the format of the talk is fairly informal. So if you have a question, put it on the chat though. Like, let's not interrupt him for the first 20 to 30 minutes. And he himself will ask you, and then you can unmute and ask. Okay.
All right, great. Thank you so much, Satara. Wow, such pressure of being the opening act for Space Week. Oof. Anyway, yeah. So the thing is that today's session is actually a part of this 3 day workshop on space mission design that I usually do. And the thing is that because of like some circumstances, I wasn't really able to cover the day one part. So here's the thing, right? I know some of you are in school, some of you are doing your BScs in physics, some of you are like aerospace engineers, some of you are doing your masters and everything. So we have like a pretty mixed bag of audience. So the thing is that I want to talk about a lot of interesting stuff, and but before we get to that, I need to establish some definitions, some terms, some ideas, so I know that we're all on the same page. um, so if for some of you what I'm going to talk about is redundant or simple, I hope I am able to like talk about the same stuff that you people have learned with some different geometric insights or something like that. But before I even start anything, I wanted to share two videos of trajectories by two very well-known spacecrafts. So I don't know how many of you know about Cassini, and I'm sure almost all of you know about Voyager 2. A lot of Carl Sagan fans in here that I've seen. So I'll start with Cassini's. I'll share my screen, and um, yo, why can't I find this? Do I have to share my whole screen? Okay. Can you see my screen, Sadara? Can you just like confirm if you can see my screen?
Yeah, we can see your screen.
All right, great. So Cassini was obviously a space mission to Saturn, and the thing is that Cassini had different stages of its missions, and it's not, a lot of people have this fairly simplified idea that okay, a spacecraft goes to a planet, it orbits there, and then it comes back. But the idea is that all of this is so expensive, we can't send spacecrafts again and again to some planet, right? So we want to maximize how much research and how much data we can do with our one mission. So the orbits were designed in a way that Cassini observed Saturn up close and then from far away, and then it observed the poles of Saturn, it observed the equatorial plane of Saturn, and not only that, it also observed various different moons of Saturn. So it kept changing its positions, its orbits around Saturn, and Cassini was able to do what multiple different spacecrafts would have been able to achieve in different missions, just because the orbits were designed so meticulously, so cleverly. So I'll just show it to you. It's a very pretty little thing, in my opinion. It looks very complicated. It looks very intimidating, very overwhelming. That how did people even think to do this? And you'll see that there are different colors, and the different colors represent different parts of Cassini's mission. So yeah, it's called Cassini's ball of yarn because it starts looking like a ball of yarn eventually. um, but again, as you may see that there's a lot going on here. It's not just like going in a circular orbit around Saturn and doing the same stuff. There it has a very interesting trajectory. It goes around, it goes to different places, and it tries to collect as varied of data sets as possible. And this is one example of clever orbit design, in my opinion. The other is obviously Voyager. I also wanted to talk about Hayabusa 2 by JAXA, which went to the Ryugu asteroid, which is by far one of my favorite space missions ever. But we'll see if we get time. I'll talk a little bit about Hayabusa 2 as well. So this is so I'm skipping ahead. So that's when the more interesting part happens. The thing is that Voyager 1 and Voyager 2 have left are in the interstellar medium right now. They're not exactly parts of our solar system anymore. And to do this, they required an enormous delta V. And what is delta V? We'll eventually come to that. But the idea is that to get far and far away from our sun's gravitational influence, you need to have a lot of uh, you need to have a very high velocity. And the problem is that for gaining velocity, you need fuel, and fuel is heavy. So you can't launch with a lot of fuel in space. And because you can't launch with a lot of fuel in space, it's also difficult to gain a lot of change in your velocity, to increase your velocity too much. But again, these probes managed to do that. And how did they do that? They use this very clever thing. Again, we'll talk about it in much greater length, called a gravitational slingshot. And you'll see what happens. And it looks pretty wacky, in my opinion, that suddenly the spacecraft just changes its direction and speeds up, and I'm like, whoa, what happened? So I'll start this off. um, just keep a lookout for the outer planets, right? Just notice what happens when Voyager 2 meets Jupiter and Voyager 2 meets Saturn. And again, this they managed to do this because of a very rare planetary alignment. They went on this grand solar system tour, clicking pictures of Jupiter, Neptune, Uranus, a lot of different planets from a lot of different positions. They gave like, yeah, okay, now here's Jupiter. I will stop talking. Something happened to Voyager 1. It changed its direction. Again, something happened to Voyager 2 and it sped up and changed its direction. And what I was saying was that the rare planetary alignment was such that the gravitational slingshot from Jupiter sent it on a trajectory where it would intercept Saturn and take a gravitational slingshot from Saturn. And the gravitational slingshot from Saturn sent it on a trajectory where it would intercept the next planet, Uranus. And it would take a gravitational slingshot from there, and then from Neptune, finally exiting our solar system. Um, So again, Voyager 2 managed to do something which is an incredibly difficult feat for most spacecrafts. And it managed to do not because of our technological abilities, not because we had like such massive engines, because it carried so much fuel, or because of brute force that, okay, we just built a huge rocket and then we sent it with a lot of fuel. But because of clever, I'm so sorry, I'll just because of very clever orbital design, and because of very clever space mission design. Yeah, it's definitely very beautiful. uh, is it moving clockwise or anti? Oh, are we going to see the gravitation? Yeah, we did see the gravitational assist. So the gravitational assist is called the Kuiper Oberth maneuver. It's more like Kuiper maneuver and exploiting the Oberth effect. We'll get to all of this eventually. So I hope that I could inspire you to just like just like get the idea across that designing a spacecraft's orbit is not just planning out where you want it to go, where you wanted to go. It's a lot of clever tools and tricks which we get to utilize to be able to do a lot more than what our technologies currently support. So again, I'd like to keep this informal, so I haven't really prepared a presentation, but yeah, I do have certain topics that I wish to cover during this talk, and I hope I get to cover most of them. Again, I'll use this term, which is like a term from science fiction. It's called astrogator. You must have seen all these crazy big space crafts in Star Wars or Star Trek, like the Millennium Falcon or the Starship Enterprise, or that spacecraft in Wall-E. An astrogator is someone who has the responsibility of navigating in space, of like steering the spacecraft, mapping out trajectories and stuff. So yeah, I hope to introduce you to some of the clever tips, tools and tricks that an astrogator gets to use. But before we get to that, I want to introduce like some more mundane ideas, if I may use that term. And so I'm gonna quickly cover two things. Okay, I'm gonna cover Keplerian orbital elements. So if I'm using things like argument of perigee and stuff like that, then it's not. Yeah, I said astrogator. So I'm gonna use certain terms, and just so we're all on the same page, I'm gonna help you develop some intuition about it, and I'm gonna use this game for that. Uh, this game is called this game is called Kerbal Space Program, and in my opinion, it's one of the greatest ways to learn and teach orbital mechanics. It definitely has its own little, like, it's not a realistic simulation of physics, although you can have certain realism overhaul, certain add-ons to this, so the atmosphere is more real. And one of the major problems with this is that it doesn't use like n body simulations. It uses only two body simulations, so at a point of time it only considers the gravitational effects between two bodies, not like all the planets in the solar system. But you'll see why I really like this game. Can you see my screen right now? I hope you can see my screen. Can you see my
Yes, we can
screen?
see your screen.
Okay, great. So I'm gonna what I want to do is first of all define first of all yeah so first of all define certain terms like prograde, retrograde, normal, anti-normal. What these refer to are directions in space, relative to your velocity. So what is prograde? Now if I look at my orbit, this blue line is my orbit, right? Where am I going? I'm going in so the direction in which I'm moving, if I face my nose cone, if I face myself in the direction where I'm going, then that, and then I burn my fuel. So, okay, this is our spacecraft. This is our little spacecraft. And just assume that this is the direction in which I'm moving. Okay. Now, if I burn my engines in the direction of my velocity, this then so if I'm burning my engines here in the direction of my velocity, then that is called prograde burn. And if I burn my engines in the opposite direction of my velocity, that means I turn my spacecraft around and then burn in this direction, then that's just called retrograde burns. Okay, I hope it was clear. In the direction of my velocity, it's prograde burns, and in the opposite direction of my velocity, it's retrograde burns. So if I burn in the direction of my velocity, I'm speeding up. If I do a retrograde burn, I'm slowing down. Okay. The other thing is normal and anti-normal. And now, what is normal? Normal is burning perpendicular to your orbital plane. Okay, so if this is the direction in which I'm moving, this is the direction in which my spacecraft is going, and I turn myself perpendicular. I turn my engines perpendicular to my orbital plane, and then burn my engines perpendicular to that. Then that's called a normal burn. So this would be a normal burn. And again, anti-normal is pretty easy. If I turn in the opposite direction, again perpendicular to the orbital plane, and then do a burn there, then that's called an anti-normal burn. Okay, we'll get to what all of these things do. Okay, you know what? I'll just talk about it right now. So here's the thing: what are all these what are all these burns, right? What do they even do? So suppose I do a normal burn. Okay, this the triangle here represents a normal burn. Suppose I'm burning perpendicular to my orbital plane, then you'll see that I'm doing this thing. I'm raising the inclination of my orbit. The angle here, I'm raising the inclination, right? And if I do an anti-normal burn, then I'm lowering my orbit in a sense. What this means is that suppose I suppose this is a telecommunication satellite, and I wanted to cover uh, these higher latitudes, right? Then then I need my spacecraft to be able to reach those latitudes. So lowering the latitude and longitude. Again, lowering the orbit can refer to different things. It can refer to lowering apoapsis, periapsis. In this case, I'm referring to a very specific thing that's called the inclination of the orbit. And I'll formally define this again when I'm talking about the classical orbital elements. But I hope I could give you some sense of what normal anti-normal burns do. They change the inclination of your orbit. Okay. Now, what does a prograde burn do? So there are reasons why prograde burns or retrograde burns are generally done at apoapsis and periapsis. So apoapsis is the point where the spacecraft is the farthest away from the central body. Yeah. In this case, it's Earth. And suppose we're here at our apoapsis. Okay. So at apoapsis, the spacecraft is traveling slowest, and at periapsis, it's traveling the fastest. Now, there's this thing called the Oberth effect, which which is a very easy thing to derive for yourself. But the general idea is that the greatest efficiency in the change in kinetic energy you can achieve when your velocity is at the maximum. So let's just get to our periapsis and do a maneuver there. A maneuver is basically any sort of burn, right? Now we're here at our periapsis and we're doing a prograde burn. I want you to observe what happens. I'm doing a prograde burn, and burning in the direction of my velocity raises my apoapsis. It raises the point. My periapsis is still there. It just raises my apoapsis. So if I have more delta v, like the higher change in the velocity, the further away I can take my apoapsis to be. The same goes here. If I'm at my apoapse and I want to circularize my orbit, then what do? I I'll add a maneuver here at my apoapsis, and I'll try to raise the other node of my orbit. So with these two burns, this is essentially what's called a Hohmann transfer, and again I'll get back to it eventually. But this is essentially how astronauts reach the International Space Station. So what they do is they reach an orbit, then they at one node they raise the apoapsis, and when they reach the apoapsis they do another burn to raise their periapsis to circularize their orbit. So again, I hope I could tell you, like, give you some sense of what happens, why this happens, and all this stuff we'll get back to. But I'll stop sharing my screen right now, and I want to cover Keplerian orbital elements as well. So I'll just get to that. I have seen it before, but anyway, thanks for searching it up, Voyager. Okay. Okay, yeah, no. So what are Keplerian orbital elements? Now there are 6 classical elements which are used to define an orbit and the position of the spacecraft in that orbit. And what are those? So one thing which is pretty obvious is so we all know Kepler's first law, orbits are ellipses, right? So one thing is how big the orbit is, and how big particular ellipsis can be given by its semi-major axis. So semi-major axis is the longer axis divided by 2. So the semi-major axis is the first Keplerian element. I I think I can use STK to develop more intuition about this. but I'll open it. Until then, I'll just talk about it. So one of the Keplerian elements is the semi-major axis of the ellipse. The second is the eccentricity of your orbit. And again, I think most of you must be familiar with what eccentricity is. It's the squishification of an ellipse in a sense. So, like how circular or how squished the ellipse is, right? I won't spend too much time on these things because I'm assuming you're already comfortable with this. The third thing, again, which we saw right now, is the orbital inclination. So we have Earth and we have an equatorial plane. Just assume that there's a plane which cuts Earth's equator, right? Now you can have a spacecraft orbiting on this plane, or you can have a certain difference in the angle between the equatorial plane and the orbital plane of your spacecraft, and this angle is called the angle of inclination. So this angle of inclination in like Earth monitoring or Earth related satellites, it is directly involved with what kinds of latitudes it gets to cover. So the orbital inclination of a particular orbit of a spacecraft is the maximum latitude to which the spacecraft can go. And inclination is super important, right? Because again, you might have, I don't know if you remember the first SpaceX launch where they launched astronauts, the first commercial crew with like Bob and who's Doug, I guess, right? Just correct me if I'm wrong. This launch happened very recently, right? And they had to scrub the first launch because of weather conditions. And some of you might have thought, okay, the weather cleared out in the next 30 minutes. Why didn't they launch in the next 30 minutes? The reason why they didn't launch is because to rendezvous with something in space, so to rendezvous is basically meeting a certain body in space, right? And to dock with this International Space Station, you need to meet the International Space Station. To rendezvous, you need to have the object that you wish to dock with right above you when you're launching. Otherwise, the inclinations wouldn't work out. And a change in inclination is a very expensive maneuver in terms of fuel. So the raising and lowering of apoapsis, periapsis is fairly easy compared to changing your inclination. And again, it's pretty easy to know why. And I'll suggest you should work this out yourself doing the mathematics. At the end, I'll recommend some of the textbooks. I actually wanted to do some of the problems in certain orbital mechanics textbooks with you, but there's nothing I can write on here. So one question: during Mars orbital mission, the burn was used. Yeah. So most of the interplanetary missions happen like this only. So I'll when I get back to Kerbal Space Program later, I'll talk about how you can possibly reach the moon. Okay, how would you go to the moon? You don't radially go outwards to the moon because that's a crazy expensive fuel maneuver. Um, so yeah, so we talked about semi-major axis, we talked about eccentricity, and we talked about inclination, and these were fairly straightforward, right? The other very straightforward orbital element is the epoch, which basically just refers to the time. Like we have a certain body. At what time are we looking at that orbit? So when you know the time and you know everything else about the orbit, then you can figure out where your spacecraft would be at that point of time. So I'll go to orbital. I'll go to STK, and again, this is one of the licenses of STK is free. So if you want to play around with this, you can download STK. It's called AGI Systems Toolkit, and it's a pretty cool software in my opinion. So I'll try to do this live with you people. So what we want to do is, okay, let's just let it load. I think I'm doing a little too much on my computer with STK and Kerbal Space Program both together. Uh, this is embarrassing. I'll get back to this once STK starts. I'm so sorry. I'm so sorry. So yeah, this is called STK, AGI STK. Yeah, it's working now. So yeah. What I'm gonna do is I'll set an I'll just insert a satellite with certain orbits here, right? And I don't want the orbit to be circular. I want to have complete control over what I want to do. And now the things that you see here, right? The six elements here, these are the orbital elements in a sense. So we talked about semi-major axis. It's how big your um, how big your orbit is, how like literally how big your orbit is. We talked about eccentricity, like how squishy-fied your ellipse is. We talked about inclination, what's the angle between the equatorial plane and your orbital plane. And now we want to think about what these things are. And we also talked about the anomaly, like we also talked about epochs. So I'll get this orbit here. And now we can see that there's this circular orbit revolving, there's the satellite revolving around the Earth. What I want is, let's just think, let's just raise, uh, let's just get a bigger circular orbit so that so the things that we're doing with it won't necessarily intersect Earth. And now we have a bigger circular orbit. Oh, sorry. No, wait. Uh, this shouldn't cause an issue. Okay. Wait. I don't know what happened. Oh yeah. I didn't zoom out. Wow, this is so stupid. just I don't know what's up with this one here. So we have our circular orbit here, right? This is fairly circular. What is going to happen if I change my eccentricity? Can anyone like unmute and tell me what's going to happen if I change my eccentricity? 0 is a perfectly circular orbit. What happens if I turn this to maybe 0.5? Does anyone want to guess? Just unmute yourself and say, tell me.
It will become an elliptical,
Yeah?
an ellipsoid maybe.
Shape of the orbit changes as the eccentricity changes. Like then it will form elliptical to all
Yeah,
other structures.
exactly. So as you might have noticed, it's not as circular anymore. It's more elliptical. It got a little squished. So what's the next thing here? Now for this satellite, let's set our inclination to 0 degrees. So we have some reference point, okay? And we'll get another satellite. So 0 degree inclination means it goes right over the equator. And we'll get another satellite um, with an orbital inclination of certain degrees, 45 degrees. Cool. I just don't want it to be. Okay, 28.5 works in my opinion. Also, everything else should remain the same. 36,000, 0.5. Yeah. So there, if this was our equator line, we raise our inclination and then this changed our orbit, right? What else can we do with this? I'll just remove this. You know what? Let it be. Let's talk about argument of perigee. So what does that mean? So there is a line. There's a semi-major axis, right? There's going to be a line connecting your apoapsis to your periapsis. Where is that line pointing? This is basically something that controls that. And again, like the reference frames are important here. But so you see everything else is same between these two orbits. But here it's pointing in this direction. Here it's this one is 45 degrees offset. And like how are we calculating argument of perigee? Like what angle is it? This angle is from the vernal equinox. Again, like I don't want to take too much time about this. Just like I hope I get the point across. Like where is your argument of perigee line pointing? that is what's given by like where is your perigee line pointing, your semi-major axis pointing, that is given by the argument of perigee. What else can we do with this? Now, as you might have seen, let's just set everything again back to 0, so that both of our orbits are both of our orbits are similar. And I'll raise my inclination again to, let's say, 45 degrees, right? What this is going to do is it's going to cut the equatorial plane. Our orbital plane is going to cut the equatorial plane. There is another degree of freedom which is available to us. Where do we want the orbital plane to cut the equatorial plane? Because there are only going to be 2 points, right? So there's one when it's ascending, one when the satellite is going from the southern hemisphere to the northern hemisphere. There it's going to cut the equatorial axis once, and the second time when it's descending. So the right ascension of the ascending node, right extension of the ascending node, is also like sometimes in other, you can think about it in another sense, which is the longitude of the ascending node, which again means the same thing, like where on Earth do we want the satellite to cut the satellite's orbital plane to cut the equatorial plane. And so let's just make it, okay, yeah. So this is cutting the equatorial plane at certain points, right? Now, again, there is a more formal way to define all these terms, but I just don't want to stick with these fundamentals for way too long. But you see, okay, let's just see this. The change between the cutting here is happening somewhere on somewhere above Africa, right? It shouldn't be Africa if we're considering it to be 0. But now we can change this. We can have this at 45-degree longitude, or you know what? That would be too small for us to notice. Let's just make it 90 degrees. And now it's cutting it at some different point. See? So now the cutting of the orbital plane and the equatorial plane is happening somewhere over India. So this is another degree of freedom. Like the best way I understood this was with play, like the best way I understood about right ascension of the ascending node and the argument of perigee is by actually making a ring with a bendy wire and then playing it around, like what are the different things I can change about this about my orbit. So that's one thing. How do satellites respond to space in real time? Is the argument essentially an angle? Yeah, argument is essentially an angle. We watch those screen things in movies and web series, but now, okay, yeah. So like this was definitely not enough to properly understand the Keplerian elements and properly understand the different burn types, but this was enough for us, for most of you to probably like be on the same page with what I'm going to talk about next, which is the more interesting part. So as I said, there are certain cool tools and tricks in the toolkit of an astrogator which can enable you to do more things than you would have been capable of otherwise with only your technology, right? Like going to farther away places. So if you think about it, if I want to go to Mars, which was something someone brought up, if we want to go to Mars, one naive way of thinking about is that, okay, when Mars is closest to Earth, what I'm going to do is suppose this for a small element of Earth's orbit and for a small element of Martian orbit, we can think of them as essentially straight lines. See, so one naive way is that, okay, when Mars is the closest to Earth, I'm just going to launch directly to Mars, which is definitely not what happens. This would have been the fastest way, but it's not the most energy efficient way. Why is not the most energy efficient way? Because the Earth is traveling around the sun with a certain velocity, right? And when you're launching from Earth, you also have that velocity of Earth. So if you launch directly above, then you're basically going to start curving outside, because you also have a inertia component in the direction of velocity of Earth in its orbit. So if you want to go directly up, then what you need to do is you need to have a velocity vector which counteracts Earth's motion. So Earth has a very high velocity around the sun. So you need to burn your engines first sideways to counteract Earth's velocity, to counteract the inertia in the perpendicular direction of where you actually want to go, and then burn your engines upwards towards Mars, which is a crazy thing to do, because you're basically trying to like, which is a crazy amount of fuel to burn to counteract your velocity in the orbit of the Earth. So why not actually use it for your own advantage? So as we saw in Kerbal Space Program, I'll again go to Kerbal Space Program now. Resume, sorry. Can you see the whole screen, or can you only see the Kerbal Space Program screen? Just want you to see KSP. Yeah, okay. So if I keep zooming out here, you see this is the orbit of the moon, right? What we might need to do is, like, obviously one way to do is that when I'm at one of my nodes, I do a prograde burn so that my orbit intersects moon's orbit, and then when I'm caught by moon's gravity well, I do another burn to circularize my orbit. But this isn't always practical, because all these burns, uh, we are essentially assuming that this change in velocity. So you'll see here that we have certain change in velocity available, 66 meters per second. This is the delta v available to us. This change in velocity we assume in our calculations to be instantaneous, but it obviously isn't instantaneous. It happens over a certain period of time, and we can only assume them to be instantaneous because these burns take shorter time compared to the time period that the satellite takes to go around the orbit. But what may happen is that these burns might not be instantaneous. If I want to change my velocity to a large extent, this may not. This is okay. It's burning my fuel. Wow, didn't notice. So these burns may not be instantaneous depending on your engine's capabilities. If your rocket engine can produce all this delta V in one go, this is what I'm talking about. Essentially, is thrust, in a sense, like how fast you can achieve your delta V. But anyway, uh, we might need to do several of these Hohmann transfers, and Hohmann transfer is one of the most efficient ways. It's, as I said, as I mentioned previously. So what we do in our Hohmann transfers is, at one of our nodes, we do our prograde burns to I'll zoom out here so we can see this clearly. We raise our apoapsis on one of our nodes. Then maybe the next time we're here, we do another burn to raise our apoapsis again. So you don't have to think about these as like once. You can do this multiple times, right? So the second time I'm there, I might do another burn to raise my apoapsis again. And then I can keep doing this until my apoapsis intersects with that of the moon, right? Right? So Kerbal Space Program does this thing that if it intersects, then it does its own little thing. So I'm not actually going to intersect my thing with the moon. But then what's going to happen is that if you don't circularize your orbit there, you won't stay on the moon. You'll come back to Earth. So you need to do another burn there to actually circularize your orbit. Okay. To circular. Oh God, this is so small. Shit. Okay, I'm so sorry. Like, uh, it's burning my fuel. I don't like this. So again, as you might have noticed, it's something which isn't exactly suitable for like a hour-long lecture. It's more like a thing that you play around with it. So the ones who can get access to Kerbal Space Program, I definitely recommend that you somehow find Kerbal Space Program, because you're going to learn more just playing around with Kerbal Space Program. It's kind of glitching on my computer right now because I'm running so many things. This all works well with ellipses, but how about circular orbits? Yeah, so if you have a circular orbit, then essentially at all points of time in your orbit, the distance from your central body is going to be the same. So uh, I I said that when I want to raise my apoapsis, I do my burn at my periapsis because at periapsis I'm traveling the fastest. In a circular orbit, my velocity throughout the orbit is going to be the same. So I can essentially do a burn anywhere in my circular orbit, depending on where I want to be when my apoapsis is raised. So so anything I do at one point of the orbit essentially really only affects what is going to happen on the other end, the diametrically opposite end of the orbit. So depending on where I want to be after my burn, after I've traveled half of my orbit, that's how I get to decide like what do I do in a circular orbit. And circular orbits are super important, right? Because in circular orbits, your velocity is not changing, and that's a pretty uh, nice thing to have. So like the International Space Station, geostationary satellites, they're all in circular orbits. Can we change the circular orbit to elliptical orbit and vice versa? Yeah, you can definitely do that. Although changing your circular orbit into an elliptical orbit while your semi-major axis remains the same, that is a tricky thing which definitely you should work out yourself. Like what we're trying to do is only changing the eccentricity and not changing the argument of perigee or argument of uh, uh, not changing the argument of not changing wait essentially what we're trying to do is only changing our eccentricity and not changing our semi-major axis, and that's definitely an interesting thing to try out. We can change our eccentricity. Obviously when I do a burn, it doesn't remain circular anymore, so I have to circularize on the opposite end of my orbit. But I don't want to raise my orbit, I only want to change my eccentricity. That's a pretty cool thing to try out. If you can just modify it, I've been use there's a free, okay. um, so this thing of doing two burns instead of going radially outwards to where you want to be. In fact, the radially outward maneuver technically only changes your argument of perigee. And again, this is something which, if you think about it, makes a lot of sense. So if I have an orbit and if I burn my engines outside, like radially outwards, it won't really take me outside because when I launch from Earth is rotating at a certain velocity, right? So when I'm launching from the surface of the Earth, I carry that inertia with me. This is why launches from the equator are so important. This is why launches from the equator can be helpful because the velocity gain from the rotation of the Earth that you get on the equator is the highest. But again, one of the things is that if you launch from the equator, then the equator is the highest inclination that you can achieve. So if you want to change your inclination, then you have to burn fuel again. And change in inclination fuels, as I mentioned previously, are very expensive. That's why it's not only important to like design your orbit, it's also super important to know where you want to launch from and when do you want to launch. And these are all things which I would love to talk about in depth, but I don't really have a lot of time. So like we'll try to do one more session of orbital mechanics so that we can talk about all these things in more detail because there's so much to talk about. uh, but let me just quickly go to the next part, uh, which is the Kuiper-Oberth maneuver. So as I said, Oberth effect is just this idea that the maximum efficiency in change in kinetic energy you can achieve when your velocity is the maximum. So the Kuiper maneuver is what is more popularly, colloquially called the gravity slingshot. Gravity slingshot. And what is a gravity slingshot? So there is maths you can do about it. Again, you can look it up on a textbook. The mathematics makes a lot of sense, obviously, but intuitively it took me a lot of time to understand. Like you can calculate this. It's going to take you 15 minutes to learn how to calculate what is the change in what is the velocity gain I'll get from a gravity slingshot. It's literally only 15 minutes that you're going to need to understand the mathematics. But idea, like why does it even happen? Why is it even happening? It took me a lot of time to understand, because I used to think of it, okay, I'm not burning any fuel, but I'm gaining kinetic energy. Doesn't that violate principle of conservation of? Doesn't that violate conservation of energy? And obviously, it doesn't. And the reason why it doesn't is the so when what you do during a gravity slingshot or in a Kuiper maneuver is you get inside the gravity well of a massive planet like Jupiter. You get inside the gravity well, and then what happens is the way I like to think about is uh, the planet drags you along with it. So the planet is traveling around the sun with a certain velocity. Because of the gravity of the planet drags you along with it, and then you can escape the gravity well of the planet. And now what you have is a part of the planet's velocity with which it was traveling around the sun and your initial velocity. So you kind of gained a velocity. One really uh, crude example which may help you think about this, like why does the slingshot even work is, suppose you're traveling on a skateboard or a bicycle and you're on a highway and you see a truck, and what you do is that you're traveling with a certain velocity and you somehow get the hold of a truck, and now the truck speeds you up. The Obviously in this case the truck is traveling with a constant velocity. Like do not think that the truck's engines are working. Just like the truck is traveling with a constant velocity. There's no friction, there's nothing in space. The truck is traveling with a constant velocity. You grab the truck, and now without you using any of the energy, you don't have to pedal your cycle any faster. You gain a certain velocity, and now that you gained the certain velocity, you leave the truck. And now the velocity that you have after your encounter with the truck is greater than the velocity which you had before the encounter of the truck. And again, if you think about it from the conservation of momentum perspective, what happened was that the truck slowed down a little because the truck's engines were carrying both the truck's weight and your weight. So the truck kind of slowed down, but because your weight was so small compared to truck's weight, it doesn't really matter to the engines that much. You sped up definitely. The truck slowed down ever so slightly. And that's the same thing that happens with gravity slingshots. So when Voyager went on its grand cosmic tour, every time it took a gravity slingshot, it slowed down Jupiter, it slowed down Neptune, it slowed down Uranus. With every gravity slingshot, this is not a trick that only the Voyager use. This is also a trick that New Horizons use. This is a very common tool in our toolkit. So every time that we take a gravity slingshot in exchange of getting a higher delta velocity, what we are giving up is basically we're slowing down the planet a little bit. But again, because the planet is so much massive compared to our spacecraft, the change in velocity in the planet isn't that noticeable compared to the change in velocity in our spacecraft. So that's the Kuiper maneuver. There's also like there's this thing called a two burn maneuver, which is essentially a like one way you can improve the efficiency of the Kuiper maneuver is by using the Oberth effect, which is when you're at your fastest, that's when you want to escape the gravity well. The other thing some people argue is that in certain cases it's even more useful to actually get deeper inside the gravity well. And the way you do that, uh, so okay so I'm going to talk about some counterintuitive stuff in orbital mechanics. So the velocity at which you're traveling in a circular orbit, that's what decides what's the radius of your circular orbit. Okay, so it doesn't matter how massive you are, because if you think about it, the spacecrafts that are docking with the International Space Station are much less massive compared to the International Space Station, but they're all in the same orbit somehow. That's because it's the velocity with which they're traveling in the orbit that matters. And now what happens is that when you reduce your velocity, when you hit brakes, when you do a prograde burn, you drop down in the orbit. And when you drop down in the orbit, lower orbits are always faster compared to higher orbits. So the moon is always traveling slower compared to the International Space Station. So this kind of blew me away, that if there's something traveling in front of you, how do you catch up with that thing? You catch up with that thing by hitting brakes. And when you hit your brakes, you drop down to a lower orbit. And because in a smaller orbit, it's going to take you lesser time to cover that orbit. So after one orbit, when you finally reach the same point again, you're going to notice that you're in front and the thing that was ahead of you is now behind you. And the same goes in the opposite sense. So when you want to get behind a certain object in orbit, what you do is you speed up. You do a prograde burn, you speed up towards that object, and by speeding up, you're essentially raising your orbit. You're essentially raising your orbit. And because we raise our orbit, it's going to take us more time to cover that entire distance. So when we raise our orbit, when we hit brakes, when we do a prograde burn, sorry, I didn't mean hit our brakes. When we do a prograde burn and raise our orbit, after in orbit, we're going to notice that even though we burned our engines towards the direction of that body, we're actually going to be behind the body. Like the distance between that body is going between us and that body is going to be greater. So there's that. So I mean, this again takes some time to properly get a grasp of. Like if I want to catch up with something, I hit brakes, but if I want to get away from something, I actually burn my engines towards that thing. What's the time now? 9. Okay. I don't think we'll be able to talk about the two burn maneuvers, how sometimes it makes more sense to burn your engines to slow down and get deeper inside the gravity well. Um, because when you're deeper inside the gravity well, you're gonna travel with a higher velocity. Okay, just okay. In the last in the last 70 seconds, whatever I said, just ignore that. Okay, we'll get to talk. I'll definitely send you some more resources to read about this stuff. What I'm going to move on to now is again more conceptual, and this is fairly straightforward. All the challenging, confusing stuff is done with now. And even if you like, I understand that a lot of what I said does not make a lot of intuitive sense, which is natural and like that's how things work in orbit. So don't stress yourself over it. I'm gonna give you a lot of resources. Most of what I learned about orbital mechanics was by myself. I did not do like a proper course on orbital mechanics or astrodynamics. So again, this is something which is possible. Like you can definitely learn a lot about this stuff on your own if you know where to start. So I'm going to talk about certain complexities in like in astrodynamics, and as an astrogator, you will have to encounter certain complexities. It's not also, oh, these are my inertial conditions, these are my forces, this is what's going to happen. I mean, this is essentially what's going to happen, but the forces are not just gravitational forces in this case, right? There are multiple different things that are working in that happen to a spacecraft when it's in orbit, and one of them is obviously the pressure because of the solar winds. So photons do carry momentum, uh, which I think it's a pretty popular project, the Solar Sail project by the Planetary Society. What they're trying to do is they have this huge sail and a small light spacecraft, and what they're going to do is sail on these solar winds using the momentum of the particles that are hitting the solar sails. So uh, it's not something which is negligible in orbit, because International Space Station, when it's doing its attitude burns, when it's trying to control its attitude, or when it's trying to take into account like how far have I moved away from where I need to be, it also has to factor in the pressure on the solar panels because of solar wind. So you also have to factor that in. And there are theoretical models, there are empirical models for this stuff, which you have to factor in when you're designing your orbits. The other thing is this other. So some of the spacecrafts use these radioactive sources of fuel, right? So you'll have like a certain radioactive material, and that's how you're getting your energy. Because far away from the sun, you can't really use solar panels because the sun isn't that bright anymore. In fact, not far away from the sun, a lot of Martian probes now use these radioactive cells. They because like if the sun's energy, like it's not that efficient to use solar panels and on the Martian surface. So what happens is that there's certain heat radiating from that part of the body of the spacecraft. And because heat's radiating, it kind of changes your attitude dynamics. Now attitude is basically your orientation in space compared to whatever reference frame you have. So it may not be enough, the heat coming out of from the difference in the heat that's coming out of the different parts of the spacecraft might not be enough to it's definitely not enough to change your orbit in the classical Keplerian orbital elements sense, but it can change the direction in which you're pointing. And because we can't really see where the spacecraft is pointing once we've launched it away, we need to be perfectly sure that where exactly is, like, if I say that, okay, I want you to do a prograde burn, and I program certain stuff in it. So the spacecraft changes its attitude to do a prograde burn. But what has happened is that the angles, the attitude of the spacecraft isn't what I have assumed it to be. So you have to also factor in how the heat radiating from different parts of the spacecraft different would affect your attitude dynamics. And some of you who are doing engineering would have, like, probably know better than me how navigation, guidance, and control are all, like, these are things that have to work together. You cannot not know where your spacecraft is and assume that, okay, I'm gonna reach where I want to be. You have to be perfectly sure how your spacecraft is oriented in space. You have to be perfectly sure where your spacecraft is before you can start your guidance procedures. In fact, there's this thing happened once where a Martian probe actually crashed because different parts of the probe were using different units of measurement. So one part of the computer thought that, okay, the burns that we're doing are counted in SI units, and the other part thought that the burns that we're doing are counted in imperial units. And that's why when it finally reached the Martian orbit, the entry was too shallow, and it burned up in the Martian atmosphere because there was an inconsistency in what the different computers thought is the location and the attitude of the spacecraft. So you have to factor in the pressure due to the solar winds. You have to factor in how the attitude dynamics are going to change because of the differential heating of the spacecraft. And again, most of what we calculate for our orbits is basically an approximation. When we're calculating, we use this uh, patched method where we don't. So when I want to design a spacecraft around Earth, maybe a communication satellite, I don't factor in the gravitational effects coming from Pluto, even though it's still there. I don't factor in the gravitational effects coming from moons of Jupiter, even though they're still there. I approximate that, okay, in my local system, the only bodies that are present are Earth. In fact, only Earth, because, like, the mass of the spacecraft is negligible compared to that of the Earth. Maybe when I want to do an interplanetary mission, what I'm going to do is that at certain distances from the Earth, I'm only going to assume that the only gravitational effects on my spacecraft are because of Earth. Then, after a certain point, I'm going to assume that the only gravitational effects are due to the sun. And then, after another point of time, I'm going to assume that only gravitational effects are because of the gravity of Mars. So, these are all assumptions, these are all approximations. And these may be really good approximations. And depending on, like, how you're doing your approximations, like what all bodies are you considering, these can be very accurate, but at the end of the day, these are approximations. So no one really factors in the gravitational effects coming from the asteroid belt when we're designing a mission to moon. So yeah, in a more complex setting, we have to, like, figure out ways how we want to go about doing the approximations. There are patched methods. Some people have figured out cool ways, like computationally efficient ways to do n-body simulations. Again, in n-body simulations, how much is the n in the n-body simulations? That's something that you have to decide. So these are all things. So there are perturbations because of the fact that Earth is not a sphere. And again, this is something that a lot of polar orbit satellites use. So when I want to have a satellite which is perfectly in the pole, a satellite which covers all possible longitudes, all possible. I want a satellite that covers all places on Earth. Okay, what do I do? One way we do this is we set the orbit to be very close to a polar orbit. Okay, and because the Earth is not a perfect sphere, it's kind of bulged in the equator. There are going to be perturbations. So every time the orbit around the pole happens, it slightly shifts. So one very clever way to cover all of a planet, uh, all of Earth by one single satellite without using fuel to change your or Keplerian elements is by launching a very close to a polar synchronous orbit and then letting Earth's perturbations do their thing. So it kind of slides off. And again, if you look about it, you probably need to like read up more about this to properly understand what's happening. But again, not all cases perturbations are bad. Some, in fact, a lot of perturbations are actually pretty useful. Like the solar radiation pressure was something that solar sail actually used. Similarly, a lot of satellites use these perturbations. Uh, and again, one more level of complexity which you can explore later is this thing. So, as I said, we assume that our burns are instantaneous, right? But the burns are not always instantaneous, depending on what kind of engines you're using. And there is one specific kind of engine which is not instantaneous at all. It is called low thrust continuous propulsion. So it's not instantaneous, it's continuous. And what people usually refer to when they talk about low thrust continuous propulsion are electric propulsion on satellites. And there are definitely science fiction-ish satellite and like rocket engines, like nuclear engines. They aren't exactly a thing right now. Although we're so close that it's painful. We're just like ever so away from a nuclear engine. But but electric propulsion is definitely a thing, and I'm going to show you a picture of what electric propulsion looks like because they look really cool in my opinion. They're probably the coolest looking, the most science fiction things that I have seen in rocket science. So I'm going to share my screen. This is this is an electric rocket propulsion system. So and again, these are not like science fiction ideas. We actually use them on satellites. In like today, there are satellites which use electric propulsion. But the thing with electric propulsion is that so one way you can change this is that one way you can change your velocity is by throwing away a lot of gases, a lot of heavy stuff, throwing as much of that stuff as you can with velocities which are as high as possible. The other way you can think about it is, which is what electric propulsion do. You take very light atoms and then you accelerate them to crazy high velocities, and then you shoot them outside. What the problem with this is that the thrust is not high because you can't achieve a lot of change in your velocity instantaneously, but eventually all this little change in velocities keep adding up. So you can't use electric engines to go to the orbit, because if you use an electric engine, no matter what your delta v is, if your thrust to weight ratio is below 1, then you can't take off. You can keep pumping out the gases from your engine for hours on end, but if the force is not greater than the force of gravity, than the weight of your rocket, you're not going to move a single inch. But in space, you don't have to worry about thrust to weight ratios, because any small change in velocity would cause any small change in momentum, any small thing that you throw away from you, it's going to cause a change in momentum. So for your body. So like if I'm floating around freely in space and if I have a screwdriver and I throw the screwdriver away, that too is going to change my velocity. So we do actually use these continuous propulsion systems, and the math for the continuous propulsion systems is drastically different. Like you can throw away all your college level textbooks in which you dealt with instantaneous burns and Hohmann transfers and bioelectric transfers and all these things, because the continuous things do not work at all in the same way. STK, the software that I use, it does have some programs that work with that simulate continuous propulsion, continuous low thrust propulsion. And there are definitely people who are working on mathematical analytical models to solve this stuff. And again, this is again something which is like on the bleeding edge of our computational abilities. So if you're interested in the more advanced stuff, you can probably look up how to develop simulations for low thrust propulsion. And well, I do feel like I rushed a lot. I'm personally not satisfied with everything that I covered, but I want to.
Maybe you can address some questions after maybe 5 minutes if you have any topic to finish off. And
Yeah,
after that, just address a couple of questions. Yeah, just check your chat once, Karthik.
yeah. Okay. So I am essentially done with all the concepts that I wanted to cover. And I'm gonna recommend you some resources so you can probably after this talk you can play around with some stuff. So first of all, Kerbal Space Program. If you can get your hands on it, Kerbal Space Program is the best thing to learn orbital mechanics. It doesn't do n-body simulations. It only does like at max two body simulations, if I'm not wrong. But Kerbal Space Program definitely gives you a lot of intuition to what exactly happens in space, and not just orbital mechanics, also like rocket engineering in a sense. Uh, if you do know some coding, and again, this is something that I generally do in my 3 day workshop thing. We try to get our hands on. We try to develop some stuff on this Python library called polyastro. So if you know some Python, you would love to check out polyastro, because polyastro is a great library. A lot of the mundane calculations of, if I burn this much fuel in this much time, how much is going to be the change in my uh, in my semi-major axis, or if I do this much burn in this direction, how much is going to be the change in inclination. All these are calculations which you should know how to do, but these are super mundane. So you can automate all of this stuff. You can design full missions on polyastro. You want to go to the Jupiter, how much fuel do you need, how what can you do to minimize the amount of this stuff. So one good way to think about this is in a competitive sense, like what's the least possible amount of fuel I can take to go where I want to go. So there's always polyastro, and as I showed you, AGI STK is one of the licenses is free. They also have a lot of tutorials, so there are a lot of resources to learn STK. And this is the most boring part probably, because all of you must already have so much college textbooks, dense textbook work. But there are certain textbooks which are great if you want to learn about orbital mechanics. So there's this one by Howard Curtis, which I would recommend. uh, so Howard Curtis has a lot of interesting problems that you can solve, a lot of solved examples too. There's Maxwell Norton, which is also pretty cool. There's also I actually made a list. I'll show you. Mm, yeah. So there is Howard Curtis. It's the book is called Orbital Mechanics for Engineering Students. I'm not an engineering student, so uh, but it still taught me orbital mechanics. So don't worry about that. Oh, I'm not an engineering student. What am I going to do with the? It's not like that. Maxwell Norton's book is called Spacecraft Navigation and Guidance. It's not so much on orbital mechanics per se, but it's more like the other part of orbital mechanics, which again cannot be ignored. There's one by K. Silvan. I think you may know who K. Silvan is. It's called Integrated Design for Space Transportation System. It's again it's not exactly an orbital mechanics textbook, but it does cover a lot of stuff. It covers parts of rocket engineering, parts of engine plumbing, and all this stuff. And there's this. It's not exactly a textbook. It's more like lecture notes, but it's called Dynamic Systems: The Three-Body Problem in Space Mission Design. And again, it's a very top level. It's a great top level view on space mission design and orbital design. Again, if you did not note all this stuff, I will I will send you a list of all this stuff, and probably, hopefully, I'll send you notes about on this lecture and like a detailed summary of what all I talked about. So if there were things that I wasn't able to properly explain today, you'd definitely be able, like the notes should help you out. So this was all I wanted to talk about today. Now I'm gonna take questions. Uh, I will start with the we'll start with the chat box, and I'll. Wow, there was a lot of discussion in chat box, so that's good. Mm. Are we going to see gravitational assist? After the slingshot from the last planet, which is the next orbit that it will take for another slingshot? No, I don't think Voyager took another slingshot. That was all of it. After the last slingshot it took, it had enough velocity to actually move towards the interstellar medium. So the thing is that even at the edge you need to have enough velocity to escape. What you need to do is you need to go from a bound orbit to a parabolic or hyperbolic orbit. So there is a certain delta v that is required to turn your bound orbit into an open orbit. And after the last slingshot, it wasn't an elliptical orbit around the sun anymore. That's why it's not coming back to us anytime soon. It's not coming back to us like in general. So it wasn't, it was, you know how when we send spacecrafts to Mars and stuff, uh, after a certain point, they're not ellipses anymore, they're open orbits. So once a spacecraft is on Mars, it doesn't come back to us. um, Astrogator, yeah, navigator in space. It's not a real word, I think. I don't think. Uh, so what else? The website is amazing. Oh, you're insane. Yes, yes, yes. Um, Did follow right hand rule or something? Mm, One question: during Mars orbital mission, the Petrate burn was used to save the fuel. I am not exactly sure about this thing. I mean, I don't. In general, I don't. Did you mean Petrate? Like, is Petrate some kind of burn that I do not know about, or did you mean one of the two things that I was talking about? Uh, Arushi Rajiv, are you there? You can unmute yourself if you want to ask this. Okay, no
Yeah.
one.
Hi. Am I audible?
Yeah, now I can hear you.
Actually, I just wanted to know something because
Your voice is breaking.
hello. Yeah. Hello.
I can't hear you properly.
Hello.
Yeah,
Is my voice clear?
yeah.
Yeah. Actually, during your lecture session, when once you explained the four types of burns, like you talked about Petrard burn, or if I'm mispronouncing the word.
So it's not Petrate. The two burns that are important in raising the orbit are prograde burn and retrograde burn. So yeah, these were the
Yeah.
burns that were
Uh,
used. So yeah,
yeah. So for like the Mars orbital mission that happened by ISRO conducted, so they used, I mean, on the philosophy of portrait burns or something, because of to save the fuels generally.
That's what they used. They also used a Hohmann transfer sort of a thing. I'll pull up a graphic so I can show you the exact trajectory of Mars mission. So Mars mission had it actually had different phases. So again, like most of what I talked about was like oversimplifications in certain senses. So I'll share my screen in a second. So this is the orbit of this is Mangalyaaan's orbit, right? So as you see that there was this orbit, and every time it reached its periapsis, it burned a little fuel to raise its apoapsis. then it came back and then burnt a little fuel to raise its apoapsis again. And it did this prograde burn several number of times until it finally was able to escape Earth's gravitational well into the heliocentric phase of its journey. Then it wasn't orbiting Earth anymore, then it was technically orbiting the sun. And then when it was in Mars, it had to get captured there. So that's when it did the other kinds of burns. But yeah, it did the prograde burns to raise its periapsis eventually.
So
To raise its
basically, they took six times of burns to just get out from the perigee and to get into the orbit of Mars.
not six different types of burns, not to get out of perigee, but yeah, six different. They had to do the same burn six different times, because as I said, right, it's not instantaneous. You can't really keep burning the engines because that would mess up the mathematics in the orbit. So they could only burn the engines when they were at a certain point. So they had this certain bracket that I'm gonna do a prograde burn when I'm here. So they did the same prograde burn, and they had to do that multiple times to finally escape Earth's gravity well. So I hope that addresses
Yeah,
you.
and even in when they landed the rover to the south pole of the moon, even in that trajectory motions also they used the same phenomena and to reach at the south pole, I guess. But I didn't understand one thing, that like once they have to reach the south pole, so when they reached at the moon's orbital area, how did they exactly landed on the one part?
Oh, how did they land on the Earth? So that is wow. So okay, again, this is like a past approach that we do. When we're near the moon, we don't think about the gravitational influence from the sun, from the Earth anymore. But one thing I can tell you is that, as I said, if you want to be in an orbit in the poles, then you, instead of going to the moon in a moon's equatorial orbit, and then changing your inclination to turn your equatorial orbit on the moon to a polar orbit on the moon, what you do is you set your transfer trajectory so that the trajectory between Earth centric orbit and the moon centric orbit, that trajectory is called the transfer trajectory. So you set your transfer trajectory in a way that when you approach moon, you by default are in a polar synchronized orbit. How do you land where you want to land? Now that's a very difficult question. It's a boundary problem, and it's a very common problem, because when we it's you don't even have to go to moon to think about this. When we're landing astronauts back here on Earth, right, when they're coming back from the when they're coming back from International Space Station, how do they, like, you can't just make them land anywhere you want. There are certain places from where you want to get the astronauts back again. So when exactly do you start entering the atmosphere? The way we enter the way we do our re-entries is by lowering the apoapsis, lowering one of the nodes, and then where the node is low enough, when the spacecraft is passing, the re-entry is gonna go through the atmosphere, and then the atmosphere is gonna cause drag and then slow it down further. So where exactly do we do this? One naive answer is that, okay, wherever I want to lower my node, I do my retrograde burn on the opposite end of the node. But it's again not that simple, because it's not like a 2D plane. You have to factor in the latitudes and longitudes in which you simulate the re-entry dynamics, and again, which is a pretty complex problem. In like the simplified version, it's worked on the simplified version of the re-entry dynamics during the summer, and even the simplified version is beyond the scope of this talk for now. But if you want to know more about how do we land stuff, apart from like launching stuff, how do we land stuff where we want to land that, uh, definitely feel free to reach out to me after this. I'll try to find some resources for re-entry as well. What program is this? I guess you were referring to STK. It's called AGI STK. It's by this company called Analytical Graphics Incorporated. The program is called Systems Toolkit. uh, we want to see the screen. Is the argument essentially an angle? this works with all. I think I covered all this stuff. Can't we have an optimal location between equator and poles where we have the right inclination and inertial velocity? It takes uh, okay. So yeah, this is definitely true that we don't always launch from where we want to launch. Like we don't do all our launches from the equators. Certain countries don't even have that luxury, right? Um, but what you were touching upon is a profound idea. So not every country can launch from the equator, and it's not even worth launching from the equator. So a lot of most of our communication satellites are geostationary satellites, right? And they're basically in the equatorial plane, but not all of them are launched from the equatorial plane. Certain satellites are launched from a certain altitude for a certain latitude, and then they do their change in latitude burns there in space. One thing that I really want all of you to try out, which is going to be a super fun activity, which will also get you used to using STK, and which will also develop a lot of intuition, is try to program Molniya orbits. Okay, what are Molniya orbits? So the geostationary communication satellites don't really work well if you're living on the poles. So the USSR people, they realized that okay, these satellites aren't really working for us. The Russian people, it wasn't working for them. So they had to figure out a clever way to make sure that they have continuous coverage on the poles as well, on higher latitudes. And that's why they came up with this ingenious thing called the Molniya orbit. And a Molniya set of orbit is basically three orbits which can give you 24-hour coverage at a certain point in the poles. And it basically, one hint I can give you is it uses the fact that a spacecraft travels faster near the planet and slower away from the planet. So try to use that hint and you install SDK and try to develop a Molniya cluster of satellites. It's going to be super fun. We don't have any control over Voyagers anymore. In fact, I don't even think we can communicate with them. The radio signals are too weak. How does planet leaves the gravity well after gaining the extra? A planet doesn't leave the gravity well. A spacecraft leaves the gravity well of the planet after gaining the extra kinetic energy. So this again is slightly out of the scope, but once you look at the mathematics, there is a very detailed discussion of gravity slingshots and Howard Curtis. Um, so essentially, the idea is that you have to figure out with what velocity are you gonna dive in the gravity well, and how deep do you want to dive in the gravity well of the planet. Depending on how much fuel you have, you can also burn your engines when you're in the gravity well to escape the gravity well. Otherwise, depending on how fast you were approaching, you can escape the gravity well without even burning the fuels. So one way to think about this is when astronauts were returning back from the Apollo mission, they had to do a re-entry which was just right. If it was too shallow, uh, if it was too deep, then what would have happened is that they would have slowed down way too much in the atmosphere, and the atmosphere drag would have heated up the vessel so much that it would have burned up. If it were, but on the other case, which is important to us right now, if it would have been too shallow, then the slowing down would not have been enough to actually get captured in the Earth's gravity well. So it would have just whooshed past by. So this is an example of like how if depending on how deep or shallow your entry is in the gravity well of the planet, you have to set like this is something that you have to decide beforehand. And again, this is not very complicated, at least initially, if you're not thinking about the coordinate system and the change in reference frames and the reference frame transformations. But if you look at Howard Curtis, you have a pretty good discussion there. Uh, Retrograde burns reduce radius. Yeah, it's not radius, it drops down the other node wherever you're doing your retrograde burn, because radius is only a term which is used for circular orbits, right? But the orbits are actually elliptical.
Actually, I was correct. I was you had said prograde burns reduce the other node at that time, so I was just asking.
Oh yeah, I'm so sorry.
Slip of tongue, I guess. It's fine.
Yeah. In fact, I'm sure that I would have messed up periapsis and apoapsis as well a couple of times. Just these are not words that are meant to be used so often. uh, that's why those launches are still the biggest. Can we say we do a gravitational slingshot? We use a tiny fraction of planet's gravitational potential energy, and we get potential energy. I don't think we use planet's gravitational. Oh yeah, gravitational potential energy. Yeah. That's also one way to think about it. This was in context to Aditya's question. Also, can we calculate how many gravitational slingshots do we need to slow down a certain planet by a certain delta V? Oh yeah, you can definitely do that. I don't think the number is going to be anything feasible, but yeah, you can definitely try that out. Uh, I think I think it's gonna be more efficient if you just start crashing satellites from the other direction instead of trying to slow down the planet using gravitational slingshots. But again, I don't think you can. I don't think there's much you can do to slow down Jupiter because uh, I don't know how many of you think about this. Think about it, but one of the reasons why we don't have to worry about asteroid impacts so much is because a lot of asteroids get cluttered around Jupiter's Lagrange points. So Jupiter actually saves us from a lot of asteroids because it kind of attracts a lot of incoming asteroids and then absorbs them into itself. So if all those asteroid impacts did not slow Jupiter considerably, I don't think our satellites would do much. But if you want to do the calculations, again, Howard Curtis is a good place to start if you want to learn more about the mathematics. Since Voyager has been in space for so long time, how much will the solar photon pressure would have increased its speed? This follows the inverse square law. So after a certain point of time, you don't really. I mean, think about it this way. If you remember, I said that you can't use solar panels to produce electricity in deep space. It goes the same way with the solar radiation, solar photon pressure, because again it decays with inverse square. Um, yeah, as Vivek pointed it out. How can we be sure that the perturbations by Earth in the polar orbit allow satellite to cover the entire planet? Also, the time period would be quite long, right? Of returning to the original orbit after covering the Earth due to the perturbations. So, first of all, time period does not depend on the inclination. Time period only depends on your semi-major axis. Again, one of the Kepler's laws. The second thing is that again the perturbation mathematics is kind of complicated. It's this thing called geoid harmonics. You basically use an expansion. You use a series expansion to you don't approximate using certain things. You use an expansion, and that I can send you a few papers on how the perturbations change orbits when they're near the poles, but this is kind of hard to understand intuitively unless you do the mathematics, and the mathematics isn't that straightforward depending on what level you are at. Um, while a spacecraft docks with ISS, it changes the inclination. Not exactly, because one thing is that when you're doing a rendezvous in space, first of all, you change your coordinates, your reference frames, and everything. You even use different graphs to do the docking. But one thing that you have to achieve is that there's this bracket, like the relative velocity between the spacecraft and the ISS has to be very low. You can't bash into the spacecraft. Even though there are like paddings and everything, you try to slow down as much as possible, not absolutely in reference to your orbit, because if you slow down way too much, then you're going to change your orbit. But what you try to do is you try to match your speed with the International Space Station. And that's why you need these things. Apart from doing the Hohmann transfers to raise your orbit dhire dhire to 400 kilometers, you also need this thing called the phasing orbit, where you stay there until you synchronize your orbit with the International Space Station. So when you're reaching the International Space Station, you're not there with a lot of velocity. Again, the inclination does not, depending on where the docking happens. again, I mean, changing in inclination, this is the relative velocity is way too less to actually do any considerable change in inclination. The attitude dynamics definitely change. So the orientation of the International Space Station definitely changes depending on whether or not something is docked with the ISS. Thank you so much for the notes. So yeah, I'll definitely ping the name of the books in the Discord. How does Voyager get to know when to burn the fuel to? Part of it is pre-programmed, part of it is not. So when some stuff are uh, okay, what you need to do is you have a certain trajectory that you have decided that okay, this is where I want to be. But what you'll see is that you won't exactly be on that trajectory. So at different points of time, you ask the spacecraft for its coordinates, like where are you, spacecraft? Depending on the spacecraft's position, you ask the spacecraft to do certain burns to get back to its original trajectory. And a lot of these times, these burns are not with the main engine. These burns are caused by RCS. These burns are caused by a different type of fuel. They're not the main rocket engine. Um, so so a part of it is pre-programmed, like the general trajectory is pre-programmed, but the control part of the thing happens like you need to do that continuously at certain intervals to make sure that you are going where you want to go. So I guess that was all the questions. uh, an astronaut's life is basically hung up on a set of equations. Yeah. uh, Thank you so much. Thank you so much, everyone. This I think this lasted a little longer, and I personally am not very satisfied with this. I don't know how to stop the recording and stuff. How do I record? Stop live